I will travel where no man has dared to go.
The accepted laws of physics break down.
Boundary between the known universe and a place beyond the reach of science.
All right. Hello, everyone. I figure that maybe making a video might be the best way to help everyone get some help. That's a great sentence. But with the size of our classes, it's hard to get some one-on-one time with you guys to sit and explain. I know it's always nicer when someone can just reach out and talk to you directly. So hopefully this will help. Almost the same sort of thing until we get over these giant class sizes. So the first thing we're going to do is we're going to create a problem. Okay, I'm going to show you how to actually use the moving man and how it works to help you out. All right, so here's our problem. Lorenzo, the moving man, that's right, I named him, accelerates at 0.5 meters per second squared for 6 seconds. After that time, he stops accelerating and continues on at a constant velocity for 5 seconds. What is his total displacement? Alright, as with any problem, the first thing we want to do is we want to call out all the information that we know. So we know Lorenzo is going to accelerate at 5 meters per second squared. And we know he's going to do this acceleration, what I'm going to call as T sub A, for time and accelerating, for 6 seconds. And of course, it wants us to calculate displacement. So that's what we're looking for everything. And we must realize that if we have an acceleration, that displacement will be different. We'll have to calculate it in a different manner than ones that don't have acceleration. So here, we're going to set up to be able to solve for our displacement with or while accelerating. Alright, so that's the first part. But from the first part, we're also going to find what speed he'll get to, which in the next part will be our V average. So we show V average by writing a line just over it. It means our V average. It means there's no acceleration. So what he's going to do on the average. And of course, we were also told that he will run this time, okay, which we'll call time V average, for a total of 5 seconds. So that's going to be our second part to give us displacement. So we have this first part here where there's acceleration, right? Displacement will be a bit different than the other part where there's no acceleration. So displacement will be different. So in order to solve this problem, I can start out by writing acceleration is equal to a change in velocity over a change in time. And we know that our time initial is 0. Time is 6 seconds total. So we don't have to worry about that. So I'm going to expand this even further. I'm going to break open my delta. And as always, a delta means the final minus the initial. Where I ended minus where I started. So I'm going to break that open a little bit to give me a VF minus VI divided by delta T. And then I'm going to rewrite the problem again to solve for it. Because right now we're going to solve for a V final because we need that for our next step. So our V final is equal to the V initial plus the acceleration multiplied by time. And all it just means is the speed you started at plus the amount of speed you gained from accelerating over amount of time. That's going to be equal to what your final speed is. So in this case we have 0.5 times 6. Because our VI was 0, and that gives us a final velocity of 3 meters per second. I'm going to write it over here because our final velocity will now be our average velocity, because in the second part of the problem there is no more acceleration whatsoever. So for that second part of the problem, it's just going to be 3 meters per second for 5 seconds. So now let's go ahead and solve for our displacement while accelerating. You might wish to, there's two equations you can use. You can use the VF squared is equal to the VI squared plus 2AD. Okay, because we know all that information. Or I'm going to use the delta x displacement is equal to the VI times t plus the 1/2 AT squared. As I said, you can take maybe a different approach to it and we should wind up in the same spot, just like directions. There's many ways to get to them all. But I'm going to cross this part out. Cross this part right out here because that is VI is 0. And remember, this is what I'm solving for. It's my delta x while I'm accelerating. So I can rewrite it over again. Since I cross out the first part, just to be delta x is equal to 1/2 AT squared. Now if I punch in some of my numbers, I have the 1/2 acceleration, of course. This part, first part was 0.5, and then the time we do it is 6. So I square that, and I'll get 36. And then I just think 36 times 0.5. 0.5 means half, so that's 18. And then I have to go ahead and half it again. And if I half 36 twice, I get 9 as my answer. So his displacement while moving is going to be 9. Now we just need to solve. So that's what he solved just while he was, or how much ground he covered just while he was accelerating. So now, and let's see, we'll use white. We're going to solve for the displacement here. And this one, since we have an average velocity, is very simple. It's just going to be velocity is equal to displacement over time. And I'm going to rearrange and solve for that. And I'm going to say, okay, so we're solving for delta x, which is equal to TV. Well, we can think about what we know, and we already know that it took him 9 meters to accelerate to a speed of 3 meters per second. So I'm actually going to expand open the displacement, the delta x. And as we know, delta means final minus initial. So I'm going to take the displacement final minus the displacement initial. So it's really, where is he going to wind up and where is he starting in this part of the problem? We know that he's already starting at 9 meters based on what it took him to get to this portion from acceleration. So it took him 9 meters to accelerate up to 3 meters per second. So if I draw it out, this first part here is where acceleration is happening. He's starting from 0, he's accelerating to 3 meters per second. So it's his final velocity there. And then there's going to be this next portion, which is what we're calculating for right now, where there's no more acceleration. He's just running at an average velocity. So I'm going to show that that's my x initial is 9 meters. And we're going to solve for a final. Okay, so finish deriving my equation. I'm going to get rid of xi on this side. I'm going to rewrite it again. And it'll be my final displacement is equal to my initial displacement, so my initial starting distance, plus the time I move times the velocity I move at. And TV equals distance. So if you look there, it really is just xi plus another distance equals my distance final. And I take 3 times 5, I get 15. And then I have the 9 for my original displacement. So my x final should be equal to 24. Alright, so at 24 meters. Now let's actually start to think about motion graphs and what this should look like. If we think about what displacement looks like, because it's changing, we're going to get a parabolic curve. Because see, our velocity is increasing in every single second. So we get a curve that occurs. Where in this area there's no acceleration, so my velocity will be nice and flat, which causes my displacement to become linear in its growth. There's no change in velocity, so therefore displacement steps equally. Now we're going to go ahead and we're going to run the simulator. So when I run the simulator, here's what you're going to see. I've set this to 0.5 meters per second acceleration. My velocity is at 0, right? My position's at 0. I'm going to go ahead and play this for 5 seconds. Here we go. He's accelerating at 0.5. We see him moving. We see the graph. Okay. Now here, I ran over a little bit there. Do you see that? But the nice thing about this is I can do the playback. When I do the playback, I see exactly what's happening at the similar times. So I'm going to take him to 6 seconds. And once again, if I just look at my simple math that I used here to figure out where he is, right, how much displacement will he actually cover? So the first part, he accelerates. Okay, so I'm going to blow this up so we really see the acceleration. Okay, and now I'm going to have him lose acceleration, so he's going to stop accelerating. So I'm setting it to 0. I want to click off of it. Now it just went to 0. Right? And we want to let him run for another 5 seconds. So I pause it at 6. Go back to there. And now I'm going to go ahead and hit record. And play again. And it'll take place right from this area. So we'll see what happens next for the next 5 seconds. So even now, I went over a little bit, so we should only be going to 11. So see, I let it run too far, but now it's a nice thing. I'm going to take it to where the 11 is. Oops. 11 seconds, I can see it right there. There's my 11 seconds. So if I did all my calculations, I see at the end, let's look at the relationship between acceleration and velocity. So in the problem, you can see here if I go back, when he goes, he's going to accelerate, accelerate, accelerate. This is moving in a linear fashion right here. And then once he stops accelerating, look, he flatlines because he stays at a constant velocity. And what is that velocity? It's 3 meters per second. That's what we calculated before. And this is at 0. Where he goes to normal speed then. So no more acceleration, stays constant. So now, if we get rid of this one and we go to displacement, okay, we'll see that all through this area right here, he has an ever-changing amount of displacement per second. It's got a parabolic effect right here, so it's making a kind of a loop. And we see that he's jumping up exponentially. See this? Keeps getting bigger and 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 bigger. In this part, we're going to look at how the displacement is going to change when he has an average velocity. Okay, so we can see the number we have here, and if we increase it by just 1 second, his displacement should increase by the velocity. So if it's 3 meters per second, after 1 second it'll increase by 3 more meters because velocity is constant. And we can see here, moving it by 1 second, we now have it increase by 3 extra meters. So it is a linear growth. Once again, it's something linear. This is the old parabola that we saw with acceleration. Okay, this is the second part without any sort of acceleration, how it becomes linear. And now I'm going to get rid of all of this. I'm going to take away the acceleration. Right now I'm going to play it back. And now I'm going to go to record. So I'm going to set this at 3 meters per second. Ready? And you see how we lose that parabola. Now it's just something nice and flat. And this is flat, so this gets linear. If this is flat, then this is linear. And this is curved. That's the comparison between the two. So that's how you use the Moving Man Lab, and you can go back and do all your calculations, check to see your numbers are right. You're never going to be there. So I hope this helps.